Yes, thank you. And so our next speaker will be Professor Bayle from University of Strasbourg. So Benna, you can share your screen. And in the meantime, I will give a brief introduction to Professor Bayle. He's a full professor at the University of Strasbourg, France. He has the Automatic Control Vision and Robotics Research Group of iCube Laboratory, Strasbourg. He also has the Health Tech Institute of Information Science and Technology for Healthcare, an excellence initiative program of the University of Strasbourg, CNRS, and INSERM. Professor Bayle's research interests include mechatronics design, modeling, and control of robotic systems, with a special focus on medical robotics and force feedback technology. So, yes, Benna, whenever you are ready.
Thank you. Thank you, Chao. Thank you for the nice invitation and for the organization to all of you. So I was a little bit surprised when Chao asked me for this presentation, because I had absolutely not any kind of idea that what we do here could be dexterous manipulation. So I had to think about it, and it was a great opportunity for me to think about that, and I'm going to show you what happened. But before, as we came from Stanford, maybe I'm just gonna give a few insight to the small city where we live, and maybe even if we have a couple of Nobel Prizes, maybe it's useful to say, well, Strasbourg is a town in France, in the northeast of France, with particular importance in Europe. And I'm just gonna show you what we do here. Well, in fact, we are not organized as in most American universities. We are a big group with a lot of people working together. And we are, in fact, 100 people, 40 permanent researchers and engineers dedicated to research around control vision and robotics, but with a focus on medical science and medical applications. So in this field, we have about 20 years of experience in medical and surgical robotics. And if you see on the bottom, on the top right, sorry, you can see the center of Strasbourg, with the university hospitals, and our offices are right here, so 50 meters away from the OP room. So this is a great opportunity to have such a big team with many people in the center of a medical center. And what we do, in fact, and my talk will be about that, is to be able to design complete solutions for the many practical applications that the doctors bring to us. So the idea being to guide doctors or to guide robots to analyze scenes, as you may see here, and as a whole to design complete system, because one of the issue in our activity is to be able to be multidisciplinary, combining computer vision, mechatronics, control, medicine, optics, and what is important, everything important to be able to design solutions, at least for preclinical use. Okay, so in this talk, well, I'm going to go back to this idea about dexterous manipulation and how it fits to medical robotics. And then I will develop the case of needle manipulation with two projects that we had in our lab. So, in fact, if you see this image, you understand that it fits well to the problem of dexterous manipulation. Here it's an interventional radiologist that is inserting a needle, doing what we call a radiofrequency ablation of a tumor. It's a kind of probe with a needle shape, and is doing that very delicately with his two hands. So for me, as I'm not totally familiar with the community of dexterous manipulation, I had in mind that, well, when I meet my colleagues in France in this field, generally it's about hands, robotic hands, and so on. So I had a look in the literature, and I found this very nice paper written by a team in Yale University that tried to classify and to distinguish dexterous manipulation from the concept of dexterity. So first in this paper, they go back to the historical definitions of dexterity. And I noticed here 4 different ones which sound great for medical applications. So the first one is the capability of changing the position and orientation of a manipulated object from a given reference configuration to a different one. It was by Bayle. So the second one is the process of manipulating an object from one grasp to another. The third one is about multiple manipulators, fingers, cooperation to grasp and manipulate objects, a definition given by Okamura. And the last one is the kinematic extent over which a manipulator can reach all orientations. But everything in this paper and these historical records suggests fine bimanual manipulation, hands and fingers cooperation. Well, so going back to medical application and dexterity, you can see what happens when it is necessary to make multiple motions with an endoscopic system. So very limited motions with not hands, but tools, and a lot of people doing that. By the way, these people are specialists in surgery, gastroenterology, and they can manipulate very simple tools with only 2 bending directions. So this is the state of the art in manual dexterous manipulation in surgery. So it sounds well with this historical definition of Bayle about the capability of changing the position and orientation of the manipulated object. But if you look at this type of robots on the left, which are these continuum robots very much used in endoscopic surgery, well, you will understand that there is no longer question of conventional robot plus end effector and grasper. The robot itself is the dexterous manipulation system. If I go to the second definition, well, it was about the process of manipulating an object from one grasp configuration to another. And this sounds very well for a number of very delicate tasks in surgery, and typically the suture task, which is a very complex one, for which it's impossible to do it continuously. Of course, there are some devices designed to do that, but traditionally you need to make grasp, to optimize the grasp in order to limit trauma to the tissue and so on. So many research is, well, from maybe since 20 years ago, tried to solve this problem, and it's still an open problem with devices designed to perform that. And you can see that on the right, it's not yet the solution because it's still too bulky, too complex, even though we have some computational solutions for computing the grasping in, well, let's say lab conditions. If we go to the third definitions with the multiple manipulators, fingers that cooperate to grasp and manipulate objects, of course, you have on the left the most famous surgical robot in the world, which is the Da Vinci robot, for many reasons. And you have in the right the Strauss robot developed by some of my colleagues here in Strasbourg. And it fits. It is really a cooperation between different arms that cooperate. It is not exactly what we could say dexterous from the point of view of the task that you can see here achieved, because while cutting with an electric sizer is not so difficult, but in fact the difficulty to make it simple is the dexterity of the Strauss robot. And here you can see that it allows to achieve tasks which are finally quite complex, like the endoscopic submucosal dissection. And last, well, it's another definition about Sturges, which is say dexterity is the skill in use of hands. And we have to admit that this doesn't fit to medical robotics. because all the time the surgeons, the medical, the physicians use their hands, of course, but more and more interventions are performed in a minimally invasive way. So the natural manipulation with hands has no, counterpart in medical robotics, or nearly not. To understand why, you need to know that, in fact, if you do conventional manipulation, you can look at the scene, you can manipulate tools, even if they are long. But when you do it in a minimally invasive way, as this is more and more the case in surgery, then you have, in the middle of the scene, you have what we call a trocar, which is the port through which the tool is inserted, and then the vision is no longer direct. So there are so many problems that only a few authors have tried invented dexterous manipulation with multiple hands within, for instance, the abdomen of the patient. And this is the same if you go back to the first image about needle insertion. This is not yet the issue. The issue is to try to do the best outside the body to make some manipulation, to assist some manipulations. I'm going to develop the needle insertion thing, but you just need to imagine what would happen if this radiologist was able only to manipulate with one hand. And the issues in this type of manipulation, even if it looks quite simple because it's only a needle, so it's a constant shaft, it's quite rigid and so on. There are many other problems, and the rest of my talk will be about that, and about why are we so prehistoric in dexterous manipulation in medical robotics. So to well understand what happens, I think it's useful to explain you what is the medical task. So in interventional radiology, you have a long list of minimally image-guided procedures which happen in a very constrained environment. So if you see on the right, it's an interventional radiology room, and you see this is a needle insertion, typically to perform a cryoablation, with a really limited space within and outside the gantry of medical device, in very non-trivial asepsis constraints. Well, sometimes be manual if you consider it performed by a doctor. But now imagine, compared to the image on the right, that you have to insert two robots to perform bimanual manipulation in this framework, in addition to the danger to letting this robot very near from very expensive medical devices, then you have the answer. We are not going to be able to think of bimanual manipulation. So you say, what are we going to think about? I'm going to show you. So the problem and the difficulty for dexterous manipulation comes from the tools. So there are very different shapes, sizes, flexibility. For instance, the needle you saw on the right, you saw in the film, in the movie previously, the one you see on the right, it's very specific needles with gaze tubes, and they have a hollow shaft, so they can bend very easily. So it's very delicate to manipulate. And the connection with a potential and effector is typically quite difficult. Some are flexible, and they are also very sleepy. How does it work? Well, what does a radiologist do when he performs an intervention? Well, first, planning of the diagnosis, very classical. Then a specific point that has no interest here in this talk, but we make the registration between the preoperative images and the patient in its perioperative configuration. Then the sterilization and anesthesia, and then incision at the entry point. And only after that, the needle is inserted and the treatment performed before removing the needle. Interventional radiology is the kind of manipulation you perform not in very comfortable environment. So in the more typical case that we consider in Strasbourg, the focus is to use a computed tomography, which is an imaging modality, which is very nice for its image quality and spatial resolution, which allows a variety of targets, but which has several drawbacks, including contrast agent injection, of course, the price and availability. It is also non-real time, meaning that compared to ultrasound, for instance, you have only a few images at a time for the practitioner. And the last but not least is the X-ray radiations. That is really harmful for the practitioner and limits the dose and then the number of gestures that one expert radiologist can perform. So in this very particular environment, what is important to understand for the manipulation also is that as we don't have possibly real-time control, the manipulation needs to be supervised by haptics. Well, in fact, we could show that haptics plays an important role in the control of the needle insertion. You have here the profile of a needle insertion, and you can see this sudden changes in the force experienced by a practitioner during an insertion. So these changes are kind of haptic cues that are used for security by the practitioner, and that needs to be understood if you want to perform the gesture safely. In addition to this importance of haptics, unfortunately, the interaction in terms of haptics is very complex. So it's manipulation we need to do in nonlinear environment, non-homogeneous. It is also patient dependent and very dependent on the age of the patient. And the forces are quite high. If you experience a 10 Newton force pushing a needle, you can trust me that it's really quite impressive. And well, why should we use robot and perform robotic manipulation? In fact, the potential benefits are very numerous. It can ease image tool registration, so automate the gesture. It can outperform mental human skills. The radiologists that perform such gestures are very eye trained, and it takes a lot of time, sometimes 3 years after the specialty in radiology, to be able to perform conveniently these types of interventions, especially when you have slices of the patient, okay, after the image. And so when the orientation of the needle is not in the plane, but out of the plane, it's very complex for mental representation. And as I mentioned, the gantries in the imaging device are very narrow, so robot could allow to have a better access to the patient, of course, designing very small systems. But overall, the main interest is to protect staff from radiations, removing his hand or her hand from the scene. So if you look at the system that were developed for fine manipulation of needles, but actually it's a pity, but there are nearly no commercial systems. So meaning that all the systems that we can observe up to date have been developed in the laboratories. So the result is that the interventional radiologists today only perform manual gestures. Commercial system on the left, top left, disappeared 15 years ago. The ISIS one on the top right is currently sold by an Austrian company. And the Maxio Robio robots marketed by an Indian manufacturer. These two systems, which are the only ones in the market, don't offer any possibilities of inserting the needle. And if we compare this to, well, what was observed at important points in the literature, what is important is, in fact, to be able to grasp and release the needle, to insert the needle, because this is, of course, the moment when the X-ray dose is maximum. Grasp and release is for safety, because if you hold firmly the needle during the insertion and with the patient breathing that is not controlled by a machine, then you have possible insertion, involuntary insertion. And haptics also, for the reason I mentioned. So finally, we put a lot of energy working on manipulation of needles, and we developed some systems, and you are going to see two examples of the systems that we developed through our project. The two are focused on needle insertion, which is a kind of very sharp specialty that we have here in Strasbourg. And the first one is Protect. So the idea in this project was to design a needle driver which allows grasping and releasing the needle. You're gonna see how it works to be able to be compatible with natural breathing motions. In addition to that, it was necessary to design it compatible with X-ray imaging. So you need to know that X-rays are not really compatible. CT, at least, is not compatible with metallic parts, sorry, because it creates artifacts in the images. So as only a limited part of the robot should be metallic. And in addition, if we expected to go into the MRI, it will be even worse. And finally, it was also important to have some force sensing. So for the grasping, the system uses a very special development that we did in the lab. And you can see it's based on a check. Well, if you imagine, compare to the other talks today, where you can see that people always try to seize some objects. The problem with the needle is that it's a very small object if we consider its diameter, and it's not so easy to catch. So we designed a check with concentric jaws, and in these jaws you have some part of flexibility that allows to self-center the needle when you seize it, and also to be able to hold it firmly when you need it. So this was specially designed to be compatible with this principle of grasp and release of the needle to avoid any damage on the organs and the skin of the patient. The second part that was required was to be able to measure forces. So not all the system comes in polymer, but it uses strain gauges. But for the rest, it's based on flexible arms, which were designed in polymer parts based on a Cyrus mechanism, but a flexible Cyrus mechanism, which allows for linear displacements. You can see here the displacement of the needle insertion system, which is another Cyrus mechanism, but on the left, you can observe the forces measured by this very specific sensor that was designed from polymer, and that is required a lot of modeling to be able to avoid many forms like fatigue or things like that. And then for the needle insertion, the grasping and releasing sequence is performed so as to be able to make some cycles, inserting the needle, releasing and inserting again, using grasp and release alternative motions. So in this part, there is only the actuator, which has some metallic parts. It's a piezomotor actuator, very small one. What is important in doing this manipulation is to be able to puncture fascia or interfaces between tissues. And you can observe here that at one specific moment, the needle will puncture the tissue. And this is typically what is desirable in the grasping and the manipulation, dexterous manipulation of a needle. In this case, well, I'm going to go in the plot. In this case, you can see that we have these successive peaks that can be analyzed by the user, for instance, doing force feedback teleoperation to be protected from X-rays. And this can be analyzed from the data of the force sensor by detecting peaks. Well, we have robust techniques to do that. And in this haptic interaction, in the forces that is measured, then you have all the story of the penetration of the needle within the tissue. So to conclude my talk, I asked one of my colleagues, which focused on the same topic, but with a very different technique, to provide me with some of the slides about the system that he recently designed with other colleagues. And I think that it is a good complement to this first system. This is the spirit system. So the principle of needle manipulation is also by alternating phases where the needle is grasped, is manipulated, and then released and grasped by another system. So in this case, there is not only one check, but two graspers, one which is mobile and a second one which is fixed. They are connected by a chamber, and inflating the chamber, the idea is to be able to extend and be able to give a linear motion to the needle. So doing this with a conventional pneumatic system is of course not easy nor possible in the environment. So to do that, they designed a specific compliant chamber with an inner tube to pass the needle, and an outer envelope, and of course a top surface and a bottom surface. So generally, if you inflate a system, then it will expand, but the expansions will be represented, will have as a consequence its actual contraction. So the idea here is not that, it's to be able to manipulate the needle and then to be able to make a motion as an extension. So using a very special material that I'm going to show you afterwards, which is called with negative Poisson ratio, it's possible to obtain in the same time the extension of the material when you inflate the chamber. How it works? It works based on the inverted honeycomb shape that maybe some of you know. So with this shape, if you inflate a chamber based on an inverted honeycomb, then you will have two displacements. The lateral displacement, of course, is classical, but with this negative Poisson ratio, you will also have an extension of the two faces of the system. So this system was implemented in a realistic and, well, bimaterial design, combining elastic material, which is the gray one here, allowing to get the auxetic behavior based on the deformation of the previous shape, honeycomb shape. And well, this material is quite stiff, it's a polymer, and it also allows to ensure the driver stiffness, which is generally a problem when you make a chamber, of course, in soft robotics. And the rest of the chamber is a rubber-like material used for building the hermetic chamber. So it looks like this with a needle. So one of the drawbacks is, as you may see, the length of the device is not neglectable compared to well, the size of the needle. So always the surgeon or the radiologist would like the system to be as small as possible, but it's the best that could be done using such a principle. Inside it looks like this. So you have the needle in the center. the inlets that allows the air to go into the three chambers. So I don't see if you see my mouse, but here on the top, one chamber associated to one grasper, and on the bottom, a second one, and all around the third chamber. So the graspers here in purple, the outer envelope, and between the needle and the outer envelope, of course, the inner chamber, protected, well, of course, separated from the needle by a tube to close the chamber. So here, if I play these videos, we'll be able to see how, you will be able to see this auxetic actuator pushing the needle. So it's not very spectacular, but it's very efficient. It could be a model, using an analytical model of the whole structure. It allows, well, insertion force is up to 30 Newton, and using successive displacements by 2 millimeters by 2 millimeters at a rather low pressure that is available in the operation rooms. Okay. So in conclusion, after presenting this well, special manipulation task and two systems, my conclusion is that dexterous manipulation is finally, well, a central topic in medical robotics. The manipulation of even simple surgical tools remains very challenging, mostly because of their size, shape, the environment, and because of all the constraints that are inherent to medical practice. And of course, I do not forget that I said that there is nothing to do with manual manipulation, but it's certainly a promising perspective, and I hope we'll go and study this type of crazy problem in the future. Okay, thank you for your attention. Thanks again for inviting me, and if you have some questions.